All right. Well, it's my pleasure to welcome Francesca Blando, who's going to tell us about algorithmic randomness and Bayesian convergence. So, welcome.
Thank you so much. And thank you so much for the invitation. It's a real pleasure to be able to give this talk here. What I'm going to be presenting today is part of an ongoing research project, and it's joint work with Simon Hurtiger at UC Irvine and Sean Walsh at UCLA. And Sean is here today, so he will be able to take part in the discussion later on. So let me begin with a very brief overview about what we are working on. So in algorithmic randomness, a lot of work recently has focused on applications of algorithmic randomness and computable analysis, right? And that one just takes canonical notions of algorithmic randomness and provides novel characterizations of them in terms of effectivizations of standard almost everywhere convergence theorems and analysis, probability theory, ergodic theory, and so forth. So what we are trying to do is apply the very same perspective, but this time to almost everywhere convergence theorems that are especially important to Bayesian epistemology. And in particular, what I'm going to be talking about today are certain martingale convergence theorems that really form one of the cornerstones of Bayesian epistemology and that are usually described as Bayesian convergence to the truth results because of their canonical epistemic interpretation. And I'll tell you a little bit more about that in a second. But the sort of general philosophical lesson that we are hoping to get from the results that I'm going to mention in a second is that, well, if we focus on computable Bayesian agents, namely Bayesian agents that have computable priors, then a certain type of convergence to the truth or a certain type of inductive success is attainable exactly on the algorithmically random data stream. So exactly on the sequences of observations that are algorithmically random. So let me just give you the briefest of overviews of what Bayesian epistemology is about. So Bayesian epistemology, very roughly, is a family of formal approaches to questions in epistemology that crucially relies on the idea that an agent's belief come in degrees, and these degrees of belief can be represented as probability distributions. And then from that perspective, if we think of beliefs as corresponding to probabilities, then the laws of the probability calculus act as rationality norms on beliefs. And in this context, we really think of rational learning as beginning with some prior probability distribution, representing an agent's initial degrees of belief, their initial knowledge, beliefs, inductive assumptions at the beginning of the learning process before any observations have been made. And then whenever an experiment is performed and some observations are made, then the agent has to update those beliefs, right? So usually by Bayesian update, probabilities are updated. Now, if you really think of the process of rational inquiry as being modeled within this Bayesian framework, so if you think, for instance, of the process of scientific inquiry as being modeled in this Bayesian framework, you might worry that the dependency on prior probability distributions might be an issue, in that it might threaten the process of rational scientific inquiry. And this is a canonical objection that philosophers have been worried about for a long while, right? How do we reconcile the objectivity of scientific inquiry with the subjectivity of prior probability distributions that really influence the type of probabilities that agents might have later on in the learning process? And the types of results that we look at, these Bayesian convergence to the truth results, are often used to try to address this type of worry, right? And one of the canonical philosophical interpretations is that perhaps there's a sense in which we don't have to worry too much about prior probability distributions because there is a sense in which prior probability distributions get washed out as the learning process goes on, and as the agents update their beliefs in terms of the shared evidence that they observe. Right? And I'm going to tell you a little bit more about the kind of Bayesian convergence to the truth that we focus on and the type of epistemic interpretation that they have. But this is just a nice quote by Pat Suppies, who was a philosopher of science, that sort of summarizes this general attitude towards convergence to the truth results. So here, the second part of the quote is especially relevant, so let me read it to you. He says, "The well-designed experiment is one that will swamp divergent prior distributions with the clarity and sharpness of its results, and thereby render insignificant the diversity of prior opinion." Right? So this is the general lesson that people try to draw from these convergence to the truth results. We don't have to worry about too much about diverging prior probability distributions, because after all, updating on the same evidence will eventually render these prior probability distributions insignificant in some sense. Okay, so let me tell you a little bit more about the basic setup within which we are working. So we focus on simple probability spaces of this form, where the sample space is just a set of infinite binary sequences. We have the Borel sigma algebra on Cantor space and Borel probability measures on that algebra. And we'll be working throughout with random variables of this form. I'm using this canonical notation to talk about the expectation of the random variable f relative to the probability measure mu. And in general, we are working with integrable random variables, so random variables where the expectation of their absolute value is finite. And again, because we are interested in modeling the process of inductive learning and sort of sequential learning, we're going to be restricting attention to a particular natural filtration, where for each natural number n, we look at the sigma algebra f sub n, which is just a sub-sigma algebra of the Borel sigma algebra on Cantor space that is generated by the basic open sets generated by strings of length n. And again, the reason why we look at this filtration is because each level, so each sub-sigma algebra f sub n, really intuitively corresponds to the possible pieces of information or the possible evidence that is available to the agent at the nth stage of the learning process. So it's a very natural family of sub-sigma algebras to look at in our context. Now, a quantity that is going to be especially important for our purposes is the conditional expectation of a random variable f relative to these sub-sigma algebras that form the filtration, right? And again, informally, we can look at these conditional expectations and think of it as providing the best estimate of the value of this random variable f on some input x, some infinite binary sequence x, after having performed an experiment. So after having observed the first n digits of the infinite binary sequence x. We work with a specific version of the conditional expectation, the one that I'm defining here. So if we take an infinite binary sequence x, if the cylinder generated by the initial segment of x of length n has positive probability, then the conditional expectation of this random variable f on x is just defined as this quantity over here. So we just take the integral over the cylinder multiplied by the inverse of the probability of that cylinder. And otherwise, if the measure of the cylinder is 0, we just let the conditional expectation be 0 as well. And it's immediate to see that because of the Tower property of conditional expectations, then the sequence of conditional expectations that we get is just a martingale in the sense of classical probability theory. Now, it's helpful, I think, to draw a connection between the type of martingales that we're looking at here, which are sometimes called Levy martingales, and the type of martingales that people focus on in the context of algorithmic randomness. So there's a sort of canonical way of passing from a Levy martingale of this type to a dyadic martingale in the sense that people usually use in the context of algorithmic randomness, right? So if we have an integrable random variable f and we look at this conditional expectation, then we can define a function m that takes as input finite binary strings and outputs real numbers, where for each string sigma of length n, we just set m of sigma to be equal to this conditional expectation over here, right? It's just a conditional expectation of f relative to the sub-sigma algebra f sub n on input sigma standard with the constant 0 function, right? And then everything is defined as above, right? Depending on whether the measure of the cylinder generated by sigma has positive probability or not, right? And then it's kind of immediate to see that in this context, if we define m in this way, then we just get a martingale, a dyadic martingale in the standard sense of computability theory and algorithmic randomness, because we then have that the function m satisfies the fairness property that is the sort of defining property of dyadic martingales. Now, for the purpose of philosophy, and so in the philosophical literature, there is a specific case that people often pay a lot of attention to, and that's the case of conditional probabilities, right? So again, recall that this is the version of the conditional expectation that we are working with. But if f, the random variable in question, is just the indicator function of some measurable set A, then when we look at this conditional expectation, we just get back conditional probabilities. Again, merged with this assumption that, when the measure of the cylinder is positive, then this quantity just reduces to conditional probabilities, and otherwise we just let this conditional expectation be equal to 0. Right. But we will see later on in the context of Bayesian convergence to the truth result that, the case of indicator functions is one that philosophers have been paying a lot of attention to. Okay, so we're now ready to state the main convergence to the truth result that I will be focusing on in this talk. And this is a classical result by Levy, Levy's upward theorem, sometimes also called Levy's 0-1 law, and it just states the following. I'm presenting again in the context of the probability spaces that we're looking at, but of course the classical result is stated in the context of more general spaces. But again, suppose that we have an integrable random variable relative to some probability space of this form, then Levy's upward theorem ensures two things. First, with mu probability 1, so mu almost everywhere, we have that in the limit, these conditional expectations converge to the true value of f, and we also have convergence in the L1 norm. Right? We also have that these conditional expectations converge to f in the L1 norm. And of course, from the point of view of what we are trying to do, it's this first part of the result that is particularly important, right? Levy's upward theorem tells us that these expectations converge to the truth, so to the correct value of f with probability 1. And we'd like to understand a little bit better what this measure 1 set of, in this case, infinite binary sequences looks like. So again, I've said multiple times already that this is a canonical Bayesian convergence to the truth result. So what's the canonical epistemic interpretation of Levy's upward theorem? Well, you can think about it as follows. We can think of sequences, infinite binary sequences, as being data streams or sequences of observations, or maybe, if you will, possible worlds. And then the random variable f intuitively corresponds to some quantity that a Bayesian agent with a certain prior mu is trying to estimate, right? And again, mu represents the agent's initial degrees of belief. And what is important is that the value of f might depend on which particular data stream is observed or on which particular possible world is the true one, right? And of course, when we restrict attention to indicator functions of measurable events, then the thought is that the quantity that the agent is trying to estimate is intuitively the truth value of the event of which the function is the indicator function, right? So this is why this is a case that philosophers have been focusing on a lot. And now from this perspective, if we look at conditional expectations, well, we can think of them as representing the beliefs of a Bayesian agent, right? So if we're looking at the conditional expectation of f at stage n, then we can really think of this quantity as representing the Bayesian agent's belief about the correct value of f at the end stage of the learning process, after n observations are made, after n experiments have been performed, right? And so from this perspective, you can then see Levy's upward theorem as establishing the following. With probability 1, of course, relative to the agent's prior mu, the agent's belief, these conditional expectations, are going to converge to the truth, namely to the correct value of f with increasing evidence. So as the agent performs more and more experiments, their beliefs, represented by these conditional expectations, are guaranteed to converge to the truth, the correct value of f with probability 1. Right? Now, what we're going to do next is that we're going to go through several effectivizations of Levy's upward theorem that are going to provide us with characterizations of various algorithmic randomness notions. And in effectivizing Levy's upward theorem, I'm going to be working with arbitrary computable probability measures. And again, this has to do with the intended philosophical applications of the results that I'm going to be talking about. Now, of course, there's a sense in which, from a suitably high-level perspective, different computable measures might not seem to differ too much from each other. Right? Here, I just have a couple of examples to illustrate this. So, for instance, in his PhD dissertation, I think, Kautz proves that, well, if you look at computable atomless measures, well, then there is a sense in which the class of n random degrees is independent of the particular measure, the particular computable atomless measure with respect to which randomness is defined, right? So from the perspective of the Turing degrees, there is a sense of it doesn't really matter which atomless measure you pick, which computable atomless measure to pick, even though they're technically distinct, they're not really distinct in an important way from that point of view. But of course, this is a setting that is not really relevant to what we're doing because we're really focusing on specific sequences in Cantor space and not Turing degrees. So from our perspective, it really matters which particular computable measure we're looking at, right? And again, the sort of worry that I'm trying to address here is, well, why are we not just focusing on the Lebesgue measure, the uniform measure, and why isn't that enough? Why is it that we're trying to look at computable measures on Cantor space in general? And again, another sort of related worry along similar vein that you might have is that, well, again, via an extension of the Borel isomorphism theorem, we know that any two uncountable atomless Borel probability spaces are Borel isomorphic, right? So doesn't that also tell us that, well, maybe we can just focus on the Lebesgue measure and not really worry about computable measures in general? But again, here the thought would be that, well, the Borel isomorphism theorem is not really effective. So again, we really do want to look at computable probability measures in general. And again, just to stress once more why it is that we care about computable probability measures, we're really trying to look at canonical results in Bayesian epistemology from the perspective of computability theory, thinking as computable probability measures as corresponding to the initial degrees of belief of computationally limited Bayesian agents. So we would like to be able to tell a general story that apply to all computationally limited Bayesian agents in general, so all Bayesian agents that begin the learning process with a computable prior. And most of the results that I'm going to talk about do apply to all computable probability measures, but unfortunately not all of them. Some of them will apply to computable atomless probability measures. And I'm going to conclude with a very short proof that actually only apply to computable Bernoulli measures, the biased coin tosses. And I don't know yet if it generalizes to a larger class of computable measures. But in general, our goal is to be as general as possible to have results that really apply whenever possible to all computable probability measures. If there are any questions at any point, please let me know. So this is the general shape of the results that I'm going to present. So fix some computable probability measure mu, and we're going to have that's an infinite binary sequence is random in some canonical sense, maybe Schnorr random, if and only if for all random variables on which we're imposing some specific effectivity constraints, we have that in the limit, the conditional expectations of this random variable along our sequence X converge to the true value of X. So f of X, right? So convergence to the truth in terms of these conditional expectations for all random variable in a specific class corresponds to being random in some canonical sense. Okay, and again, what's the epistemic interpretation of this result? Well, the thought is that if we restrict attention to computable Bayesian agents, so Bayesian agents that begin the learning process with a computable prior, then beliefs, which again correspond to those conditional expectations representing the agent's best estimate at each successive stage of the learning process of the true value of some random variable of interest, align with the truth in the limit under appropriate algorithmic randomness assumptions. And the thought is that when we look at different classes of random variables corresponding to different effectivity constraints, we can think of those effectivity constraints as tracking the difficulty of the inductive problem at hand, put suggestively, or a little bit more precisely, as tracking how difficult it is to approximate the values of these random variables. And what is nice from the point of view of our philosophical interpretation is that it then turns out that for natural classes of effective random variables, we can then pinpoint the collections of data streams that guarantee convergence to the truth in the sense that I've just outlined for all the random variables in the class under consideration, right? So the thought is that we can then identify the truth-conducive data streams with specific collections of algorithmically random data streams. So algorithmic randomness and truth-conduciveness turn out to align. And of course, this is just a natural continuation of applications of algorithmic randomness in computable analysis, but now in the specific context of these results that people care about in the context of Bayesian epistemology. Okay, so I want to talk about a couple of results. So let me mention a couple of effectivity constraints on random variables that we are considering. I'm sure most of you already know about all of these definitions, if not all of you, but let me just quickly rehash them. So the first class of random variables that we're looking at are the L1 computable ones, right? And a function f is L1 computable if there exists a sequence of rational valued step functions that witnesses its L1 computability in the sense that it converges to it fast in L1, which just means that it converges to it in the L1 norm at a computable rate. So the first result that we have is an effectivization of Levy's theorem in terms of L1 computable function, which provides a characterization of Schnorr randomness. Right? So again, we fix a computable probability measure mu, and for an infinite binary sequence X, we have that being Schnorr random relative to mu is just the same as having that for all L1 computable functions. In the limit, these conditional expectations along X converge to the truth represented by the limit of the step rational value step functions that approximate our L1 computable function f. Right? So again, the thought is that in the context of L1 computable functions, the function is not guaranteed to be defined everywhere, but it's just defined on a set of measure one. And so we can take these approximating function as being essentially the best that we can do, the best approximation that we have to this function f. And the result says that Schnorr randomness is equivalent to having that these conditional expectations corresponding to the agent's belief are guaranteed to converge to the truth as the evidence makes more and more observations. There is a sort of easy analog of this result for a different class of effective random variables. These are usually called integral tests for Schnorr randomness, and they're simply non-negative lower semi-computable functions that take values in the extended reals and that have a computable expectation. And there is a characterization of Miyabe of Schnorr randomness in terms of integral tests that also works for all computable measure, and that just says the following: being Schnorr random relative to mu is the same as having that for all integral tests for Schnorr mu randomness f, the value of that integral test on the sequence X is finite, right? And Miyabe also shows that there is a nice bridge between L1 computable functions and integral tests for Schnorr randomness, namely every L1 computable function is just the difference of two integral tests for Schnorr randomness, and we can of course use that to get an analogous characterization of Schnorr randomness for arbitrary computable measures in the context of integral tests for Schnorr randomness instead of L1 computable functions, right? So in that context, we have that fixing a computable probability measure mu, we have that being Schnorr random relative to mu is just equivalent to having that for every single integral test for Schnorr randomness f, in the limit, these conditional expectations, the conditional expectations of f on x converge to the true value of x, the true value of f on x. Now, These results are importantly related to a number of results that have already appeared in the algorithmic randomness literature. So first of all, our result is essentially the Cantor space analog of an earlier characterization of Schnorr randomness due to Pafak et al. In terms of the Lebesgue differentiation theorem in Euclidean space for the uniform measure, or the Lebesgue measure. So I'm stating the result here. So in many ways, our proof really consists in moving from Euclidean space to Cantor space and generalizing the result from the uniform measure to arbitrary computable measure and checking that everything sort of goes through. And again, it's sort of important for our intended application that the result holds not only in the context of the uniform measure, but also in a more general setting of arbitrary computable probability measures. There's also a few results by root that are importantly related to ours, so distinct. And I'm just going to mention a couple of them that I think are particularly relevant. So in a paper by Root from 2012, so he proves the following. So he also looks at Cantor space and at computable probability measures in general, and he has the following characterization of Schnorr randomness. So he proves that being Schnorr random relative to mu is equivalent to having that for all uniformly L1 computable martingales, now in the sort of sense of martingale from classical probability theory. So if these martingales converge in L1 to an L1 computable function, then we have that the limit of these martingales converges to a finite value. Right. And now essentially the forward direction of this proof is analogous to our result, but the backward direction is a little bit different. So if one inspects the proof of this result by root, one might note that one ends up with a Levy martingale in the sense of our result, where the value of that function on the sequence that fails to be Schnorr random is infinite, and similarly, the limit of the martingales, or the limit of the conditional expectation, is also infinite, right? So the limit fails to converge because it doesn't converge to a finite value, but it's still the case that the limit of the conditional expectation converges or is equal to the value of the random variable along that sequence. So we don't really have a failure of convergence to the truth in that setting, in a sense. Right. But for the purpose of our philosophical applications, we really are interested in convergence to the truth. So in our backward direction, we are constructing a Levy martingale such that the limit of the conditional expectations just doesn't exist, right? So we don't have that the limit is equal to the value of the random variable in question along the sequence that fails to be Schnorr random. So again, the thought is that we're really interested in focusing not only on convergence per se, but really convergence on the true value, on the correct value, because this information is important for our intended philosophical applications. There is another result due to root, which is related to ours, that I wanted to mention from the very same paper. And there he proves the following. Again, in the context of Cantor space and for arbitrary computable measures, he shows that a sequence X being Schnorr random relative to mu is equivalent to having that for all non-negative L1 computable martingales with respect to the very same filtration that we're looking at, that converge to zero almost everywhere. We have that the limit of the martingale along the sequence X is zero. And again, this result, while related to ours, is importantly different to it. And that's because of the following reason. Because of the fact that we have that the martingale converges almost everywhere to zero, there is no L1 computable function f such that this martingale corresponds to the expectation of this random variable f relative to our filtration fn. So we can't really represent this classical martingale mn as a Levy martingale. And again, that's essentially because the fact that we have that the martingale converges to zero almost everywhere forces the measure representation of this martingale to be orthogonal with respect to the measure mu, right? So we don't have that the martingale in question corresponds to a Levy martingale, which again is important for our intended interpretation. So in this case, the two results just deal with different types of martingales, so they're related, they're not really the same. Okay, so this was the first result that provides a characterization of Schnorr randomness in the context of computable measures and L1 computable functions and integral tests for Schnorr randomness. The second result that I want to present has to do with density randomness, which is perhaps a slightly less well-known algorithmic randomness notion, so I will just define it here. So again, fix some computable probability measure mu. A sequence X is density random if and only if two things occur. The sequence is modulo random relative to mu, and the sequence is also a dyadic density 1 point relative to the measure mu. And being a dyadic density 1 point is just defined here. It means that the lim-inf of the conditional probability of C relative to longer and longer initial segments of X is 1 for all pi01 classes C to which X belongs. Right. So I'm writing it in this way just to sort of emphasize the connection with Levy's upward theorem. So again, density randomness just means being modulo random plus being a dyadic density 1 point relative to the underlying measure. Now, the second class of effective random variables that we're going to look at are the weakly L1 computable functions, which I think were first introduced by Miada, though I might be wrong, and that are just a natural weakening of the notion of L1 computability that I talked about earlier. So again, we fix a computable probability measure in the background, and we say that a function f is weakly L1 computable relative to mu if there exists a computable sequence of rational valued step functions that converge to f in the L1 norm, and such that this sequence of rational valued step functions has bounded L1 variation. Right? So in the context of L1 computable function, we had that the sequence of rational valued step functions had to converge to f in the L1 norm at a computable rate, and now we're weakening that requirement, and we are only requiring that the sequence must have bounded L1 variation. And in this context, we can get an analogous result, except that now instead of Schnorr randomness, we get density randomness, right? So if before we had the convergence to the truth for all L1 computable function occurs on the Schnorr random sequences or data streams, now in this context, we have that being density random corresponds to convergence to the truth for all weakly L1 computable functions. And here there is an important weakening that I should mention. In the context of Schnorr randomness and L1 computable functions, the result was for all computable probability measures in general. And now we restrict attention to computable, strictly positive, and atomless probability measures. And of course, it would be nice to be able to extend this result to all computable probability measures in general. But the result has exactly the same shape as the one that I talked about before, modulo this restriction. And just as in the context of Schnorr randomness, we can also provide a result in the context of integral tests. Just as Schnorr randomness has a characterization in terms of integral tests for Schnorr randomness, Martin-Löf randomness also has a characterization in terms of integral tests for Martin-Löf randomness. And of course, the characterization of Martin-Löf randomness in terms of integral tests preceded the characterization of Schnorr randomness in terms of integral tests. So in the context of Martin-Löf randomness, an integral test is simply a lower semi-computable function, non-negative, which is a requirement that we can actually don't need in the context of counter space, but it doesn't matter. But so a non-negative lower semi-computable function with a finite expectation, right? So in the context of Schnorr randomness, the expectation had to be finite and computable, and here we just require finiteness. And there's a result, which I think is now folklore, that says that for computable probability measures, being Martin-Löf random is equivalent to having that for all integral tests for Martin-Löf randomness relative to mu, the value of that integral test on the sequence is finite. And again, just as before, we have that weaker one computable functions correspond to differences of integral tests for Martin-Löf randomness, just as L1 computable functions corresponded to differences of integral tests for Schnorr randomness. So the previous result naturally translates to this, where weakly L1 computable random variables are just replaced by integral tests for Martin-Löf randomness, right? So again, we restrict attention to probabilities that are probability measures that are computable, strictly positive, and atomless. And in that context, we have that an infinite binary sequence is density random relative to mu, if and only if for all integral tests for Martin-Löf randomness, we have that in the limit, these conditional expectations, so the conditional expectations of F corresponding to the agent's beliefs in the correct value of F, end up aligning with the correct value of F along X. Right? So just as we had that the Schnorr random data streams are truth conducive for L1 computable functions and integral tests for Schnorr randomness, we have that the density random data streams are exactly the truth conducive one for both weakly L1 computable functions and integral tests for Martin-Löf randomness. And again, so this result is also importantly related to a result by Miyabe, Nice, and Zhang, who provide the following characterization of density randomness in the context of the uniform measure, the Lebesgue measure, and again in the context of the Lebesgue differentiation theorem. So our result again is a generalization of that to the collection of all computable atomless and strictly positive measures. Okay, so I would like to conclude by presenting a couple of randomness notions that I think naturally emerge from thinking about randomness from the perspective of convergence to the truth. And I'm calling them Geifman-Snare randomness notion, because the very first authors to first notice the connection between randomness on the one hand and Bayesian epistemology were Geifman and Snare in the 1982 paper, where I think also the notion of weak two randomness appeared in print for the first time. But so in this paper, they really try to analyze Bayesian epistemology from a very high level perspective using logic. And they also, for the first time, drew a connection between randomness on the one hand and Bayesian convergence to the truth without really providing any characterization of specific algorithmic randomness notion in this setting. But as a sort of tribute to their work, we are calling here these notions of randomness Geifman-Snare randomness. And the natural corresponds to cases in which we have Levy's upward theorem and the special case of indicator functions. Right? So again, fix some computable measure mu. An infinite binary sequence X is going to be said to be Geifman-Snare mu random if all of the cylinders generated by initial segments of X have positive probability, and we have the limit of the conditional expectations of the indicator function of sigma 0, 1 classes converges to the true value. Right, so we have the Levy's upward theorem holds for the indicator functions of all sigma 0, 1 classes. Then we consider the weakening of that, which we call computable Geifman-Snare randomness, which is defined exactly in the same way, except that now we're looking at indicator functions of sigma 0, 1 classes with a computable measure. So again, it's a notion of randomness that corresponds to Levy's upward theorem holding for the special case of indicator functions of sigma 0, 1 classes with a computable measure. And the last notion that we have is what we call weak Geifman-Snare randomness, which is again defined analogously, except that in this case we restrict attention to delta 0, 1 classes as opposed to sigma 0, 1 classes. Now, the relation between these notions of Geifman-Snare randomness and canonical algorithmic randomness notion is rather easy to see. So here on the left-hand side, I have the randomness hierarchy, denoting by dr density randomness relative to some arbitrary computable probability measure mu. Here we have Martin-Löf randomness, computable randomness, Schnorr randomness, and Kurtz randomness, or weak one randomness. And here on the right-hand side, we have the notions of Geifman-Snare randomness. So one can see that being a dyadic density 1 point is just the same as being Geifman-Snare random. Geifman-Snare randomness entails computable Geifman-Snare randomness. So this is the notion for sigma 0, 1 classes with a computable measure. And computable Geifman-Snare randomness entails weak Reifman-Snare randomness, which is the one for delta 0, 1 classes, and none of these implications reverse. So all of these implications hold for computable measures in general. Of course, we also have that being Schnorr random relative to some computable measure mu entails being computably Reifman-Snare random, which in turn entails being weak 1 random, which in turn entail weak Reifman's randomness, and also none of those implications reverse when we're looking at arbitrary computable measures in general. And I just want to conclude with a proof of the fact that actually, if we restrict attention to computable Bernoulli measures, so the measures corresponding to tossing a biased coin, actually computable Reifman-Snare randomness and Kurt's randomness coincide. So we also have this reversal for Bernoulli measures. So let me just conclude by giving this proof very briefly. So again, we're proving that if we fix some arbitrary computable Bernoulli measure mu, then this inclusion holds, being Kurt's random relative to mu entails being computably Reifman-Snare random. So let's pick some sequence, infinite binary sequence X, that is Kurt's random relative to mu, and let U be some sigma 0, 1 class with a computable measure. What we want to show is that in the limit, the conditional expectation of this of the indicator function of U on X converges to the true value. But of course, if X is a sequence that belongs to the sigma 0, 1 class U, then the result is trivial. So suppose that X doesn't belong to the sequence, sorry, to this set. So in that context, of course, we want to show that in the limit, these conditional expectations along X converge to 0. Right? So suppose that this is not the case. Well, then there's going to be some computable there's going to be some positive rational epsilon, such that infinitely often we have that this conditional expectation on X is above epsilon. Right? But now we can use the fact that the measure of the sigma 0, 1 class U is computable to note that then there must be some computable function f, such that f of n is always at least n. And this f of n allows us to find exactly the points at which we exceed this rational epsilon, right? So the expectation of this indicator function IU, when we restrict attention to the f of n Sux sigma algebras and their filtration, is guaranteed to be above epsilon, right? And we can use this to define the following pi01 class. It's just going to be the set of all infinite binary sequences that do not belong to this sigma 01 class U, and such that for every natural number n, we have that this conditional expectation exceeds epsilon, right? Now, if the measure of this pi01 class, which I'm calling C, was 0, then because by assumption X is weakly 1 random, we would have that X doesn't belong to it. So it must be the case that the measure of this class is positive. And now for the rest of the proof, we're just essentially verifying that the usual proof of the fact that pi01 classes of positive measures contain tails of all multi-level random sequences extend to the case of all computable Bernoulli measures, right? So again, we're saying that the measure of this set is positive, and C is a pi01 class, so its complement is a sigma 01 class whose measure is less than 1. And now because C bar, the complement of C, is the sigma 01 class, we can just find a set of strings which is prefix free, such that C bar just correspond to the set of all extensions of the strings in this set S. And now on the basis of S, we're going to define the following sequence of sets of strings. So we set S0 to be just the same as S. And now assuming that S sub n has already been defined, we define the n plus first component as just being the following set of strings. So it's the set of strings that consists of concatenations of elements from Sn extended with strings tau that belong to S. Right? And now for each n, we can simply define the set of infinite binary sequences Vn to be the set of extensions of strings in Sn. And then one can see that this is a sequence of uniformly sigma 01 classes. And of course, because B0 just corresponds to the complement of C, and we know that the complement of C has measure below 1, we know that the measure of the set is below 1. And now for each of the other VNs, simple computations, and exploiting the fact that we're dealing with Bernoulli measures allows to show that the measure of each of these sets is exactly the measure of the set of extensions of strings in S raised to n plus 1, right? So we're just multiplying the measure of this set by itself, n plus 1 times. And now we can use this to make sure that we end up with a Martin-Löf test, right? Because now we can take a rational strictly less than 1, such that the measure of this set is less than that, right? Because we already know that the measure of this set is strictly less than 1. And now for each natural number n, we can just let k sub n be the least natural number for which this property holds, right? So we can be sure that we are below 2 to the minus n. And now we can define the set v prime sub n as just being v of kn, right? And now, because this natural number kn can be found computably in n, then we end up with a sequence of uniformly sigma 0, 1 classes that have a measure that is bounded in the right way. Namely, for each v prime sub n, we have that its measure is at most 2 to the minus n, which tells us that this sequence is a Martin-Löf test relative to mu. Now, how are we going to use this? Well, suppose that we have a sequence that is Martin-Löf random relative to mu. And suppose that it were the case that for all finite binary strings and for all infinite sequence, if this sequence y corresponds to this string sigma extended by this infinite binary sequence z, then z belongs to the complement of c, right? If this were the case, then we would have that for every natural number n, y belongs to v of n, right? But then this would tell us that this sequence belongs to this intersection, which is a Martin-Löf test, right? So this is not possible because it contradicts the assumption that we're starting off with a sequence that is Martin-Löf random relative to mu. So it must be the case, because of this argument, that there exists some finite string sigma and some infinite sequence z, such that y is just sigma extended with z, and z belongs to c, right? This pi 0, 1 class that we constructed at the beginning. But now, because we started off with the assumption that y is Martin-Löf random relative to mu, it must also be the case that z is Martin-Löf random relative to mu, and therefore z is also Schnorr random, right? But because of the way in which we define this pi 0, 1 class c, we have that z doesn't belong to u, but it's also not the case that the limit of these conditional expectations, the conditional expectations of the indicator function of u, converges to 0. And now this is a contradiction, because we know that Schnorr randomness for any computable probability measure whatsoever entails computable Guiffrida-style randomness, right? And this suffices to establish that we must have convergence to the truth along our original sequence. So again, just to summarize, because we know that the implication from computable Guiffrida-style randomness to Kurt's randomness or weak one randomness holds for all computable measure, and because we've just proven that the reverse holds for all computable Bernoulli measures, we have that weak one randomness and computable Guiffrida-style randomness coincides for the class of computable Bernoulli measures. And I'm not sure at this point whether this result can be extended to larger classes of computable measures. Okay, so I just want to conclude with a point that is perhaps a little bit more philosophical. So all of the notions that I talked about in the last few minutes, all of these Guiffrida-style randomness notion together with weak one randomness, of course, can also be seen as genericity notions. So one genericity entails all of these notions here on the right-hand side. And so the collection of data streams that satisfy all of these definitions not only has measure 1, but it is also a comeagre set of strings. And this is interesting from our perspective, because if you recall the description that I've given you of these convergence to the truth results, so the Levy's upward theorem, we have the convergence to the truth occurs with probability 1, but always with respect to the agents prior. And so people have been worrying about the fact that, well, this doesn't quite provide the required vindication that people were hoping to obtain, the sort of the required argument that is supposed to not make us worry anymore about the dependence on prior probability distributions, because we do get convergence to the truth, but only with respect to the agent's initial opinion. So it's still a sort of subjective notion of success rather than an objective one. And so people in philosophy sometimes argue that perhaps we should look at topology and look at notions of size that are topological, and maybe those could provide objective notions of a large set along which convergence to the truth should occur in order for these results to be satisfying, right? And of course, in general, we know very well that measure and category come apart. So there are many sets that have measure one and are topologically small, and vice versa. But it turns out that in the context of these notions, because they're notions of genericity, they guarantee convergence to the truth, both in the measure theoretic sense and in the sense of topology, right? So we have convergence to the truth, both with probability one relative to the agent's prior and on a set that is co-meager, so topologically large. So for philosophers that are worried about this kind of objection, then these randomness / genericity notions might be used to, at least to some extent, address their concerns. So I think I'm almost out of time. So let me just conclude by trying to summarize things a little bit. So I focused today on a specific type of Bayesian convergence to the truth result, Levy's upward theorem, and we've seen how natural effectivizations of this result allow us to equate algorithmic randomness with the truth-conducive data streams. But there are many more results that are relevant to Bayesian epistemologies that can be analyzed from this perspective. And for instance, right now in our project where we are focusing on merging of opinion results, there is another sort of canonical family of results that Bayesian epistemologists care about that roughly say that distinct Bayesian agents beginning the learning process with different beliefs are guaranteed to reach intersubjective agreement with probability one, provided that their prior probabilities are sufficiently compatible to begin with. So you can see how this can also have important application for the problem of addressing the dependency of posterior probabilities on initial priors, so on initial beliefs. So what we're doing now is essentially trying to apply the very same perspective that comes from applying algorithmic randomness in computable analysis to these merging of opinion results. And overall, the goal of our project really is to analyze Bayesian epistemology in general and all of these almost everywhere convergence theorems that people care about in Bayesian epistemology from the perspective of computability theory and algorithmic randomness specifically, right? So the goal is sort of twofold. On the one hand, we want to develop a computability theoretic approach to Bayesian epistemology, thinking about computable Bayesian agents in terms of agents that have computable prior, to see whether we can get more information out of these classical, almost everywhere convergence theorems results in the context of computable Bayesian agents. But also from the perspective of algorithmic randomness, it might be possible to sort of get new randomness notions and new genericity notions that might be of interest by looking at classical results that people care about in Bayesian epistemology from this computability theoretic perspective. And I'm done. Thank you.
Are there questions?
Maybe I can stop sharing.
Yeah, if I can jump in. Hi. Yeah, thanks so much for the talk. I was wondering, with this point that you're actually making at the end of the dependence, the dependence on the measure, right? And people wondering about the interpretation of that. I was actually thinking about that in following the idea that if you have two different computable measures in general, right? It's not just that they'll have different randoms. In fact, the randoms are going to be disjoint, right? So, like my first reaction, and when I saw some of those results, was that in some sense, I would almost interpret those results as saying that good experiments in the sense of the Bayes quotations are impossible, right? Because two different views, the places where they actually converge to truth are going to be disjoint. So I was wondering, about that interpretation. What do you think of that?
Oh yeah, that's very nice. I mean, because of course, I mean, from this perspective, then you can think you can think of randomness notions as providing a way of classifying the types of compatibility that is already present between the priors of different agents, just thinking of them as being pre-specific or maybe more fine-grained notions of compatibility, different from absolute continuity. And then you might want to think, well, in certain epistemic communities where the agents are such that they already agree on what counts as random, then say convergence to the truth will occur exactly on the very same data streams, and then we are in a sort of good case. But of course, in epistemic communities where we have a lot of disagreements, so the agents have priors encoding assumptions that make it so that they disagree on the sequences that count as random, then in those cases, well, we're sort of in a bad situation because, well, we will not have merging of opinions. And so I can talk a little bit more about that. I just briefly mentioned these merging of opinions results at the end. And we'll also have that each of the agents individual will believe that with probability 1, they converge to the truth, but actually the data streams along which they converge are completely disjoint. So yeah, I think that, you know, there are two possible stories that we could tell. And I guess my preferred version is that algorithmic randomness and computability theory really gives us the tools to classify the types of compatibility that is present within epistemic communities in a more fine-grained way, and it also allows us to to understand a little bit better exactly what kind of data streams different Bayesian agents expect their beliefs to converge to the truth on. So again, I see it really as a tool that allows us to get a better sense of what's going on in these cases. Thank you for the question. And Sean, if you have anything to add, please feel free.
Oh, I might just briefly add, you know, if we got a characterization of, say, a church stochasticity in terms of a convergence to the truth notion, that's a little bit of a coarser grained equivalence relation. So there might be more possibility for different communities to sort of converge and merge in that sense.
Are there some other questions? Well, if not, I think we should thank Francesca for her very nice talk.
Thank you so much.